Okay, so in section 3.2, number 21, we are trying to determine whether Rolle's theorem can be applied to f on the closed interval from a to b. A to b in our case is 0 to pi over 6. Our function f is f of x equals 6x over pi minus 4 times sine squared of x. If Rolle's theorem can be applied, find all the values of c in the open interval from a to b such that f prime, or the derivative of f at a value c, is equal to 0. If Rolle's theorem cannot be applied, explain why not. So, the requirements of Rolle's theorem is that f of our endpoints are equal. F of a equals f of b. The other requirement is that it is continuous on the closed interval, so continuous on the closed interval, and differentiable on the open interval. So, the other part there was that f of a should equal f of b. So let's see if our three requirements are indeed fulfilled. First off, let's evaluate f of 0. That is going to be 6 times 0 over pi minus 4 times sine squared of 0, which is going to be equal to 0 minus 0 equals 0, because sine of 0 is 0, and 6 times the 0 is going to be 0 as well. So we have 0. On the other endpoint, f of pi over 6, we want to make sure that that is also going to be 0. So this is going to be 6 over pi times pi over 6 minus 4 times the quantity of sine squared of pi over 6. If you remember your reference angles, and hopefully you do, this guy obviously pi cancels out with pi, 6 cancels out with 6, I'm left with only 1. They're reciprocals of each other, so when I multiply by them, you should get 1. And this is going to be 4. Pi over 6 is the same thing as the reference angle of 30 degrees, right? And for 30 degrees, sine is 1/2. And I'm not going to put my little chart up, but it's what I usually do in my head at least, right? Squared. This is going to be 1 minus 4 over 1 over 1 squared and 2 squared, so it's 1 over 4. So that's going to be, the 4 cancels out there. I get 1 minus 1, which is 8. That's 0. So the first part is satisfied. Check. F of a is indeed equal to f of b. Is it continuous? Well, I have 6 over pi times x. That's continuous because it's a polynomial. I know that sine is continuous. I know that x squared is continuous. So sine squared is continuous because that is just a composition of functions, both of which are continuous. And then I have the addition of two continuous functions, which would also be continuous. So, hey, check. Right? And then differentiable. Well, let's find its derivative. F prime of x. Well, the first part, 6 over pi. Remember that you can take this whole part right here and think of all of the constant multiples that occur. This is the same thing as 6 over pi times x, this first term. So, finding the derivative of some constant multiple of something, you just bring that constant multiple out and then multiply by the derivative of that thing. So the derivative of x is 1, so the derivative of 6x over pi is just going to become 6 over pi. There we go. And the derivative of 4 times sine squared of x. Let's consider that negative 4 a constant multiple as well. So we'll bring that out. And we want to find the derivative of sine squared of x. You can either use the product rule or, more appropriately, use the chain rule. So the chain rule says 6 over pi minus 4. I have my outer function is something squared. My inner function, that something, is sine. So I bring down the 2 times 2. I multiply by, I decrease this power by 1. So it's just going to be times sine of x. And then I'm going to multiply that by cosine, because that's the derivative of sine, according to the chain rule. All right? So f prime of x is going to be equal to 6 over pi minus 8 times the sine of x times the cosine of x. So actually, there is no value that this function isn't defined for, right? So especially not on the open interval, I could put any value of 0 to pi over 6, not including 0 and pi over 6. I don't need to put them in there. And it's differentiable there because I can take a number like pi over 8, let's say, and put that into here, and I would get out another number, right? So, since both of these functions are continuous just about everywhere, and defined just about everywhere, and actually everywhere, so my function is differentiable on the open interval. So my f of a equals my f of b. I'm continuous on a closed interval. I'm differentiable on the open interval. So I know that Rolle's theorem applies here. So I know that there's going to be at least one point in 0 to pi over 6. We'll call that value of xc, where the derivative is going to be equal to 0. So the book says that we need to continue and saunter on and find that value of c. So that means finding 6 over pi minus 8 times the sine of x times the cosine of x equal to 0. What values of x can I use? Alright, let's try it out. We will subtract 6 over pi on both sides. So I will get negative 8 times sine of x times cosine of x equals negative 6 over pi, and divide both sides by 8, so I get sine of x times cosine of x equals, let's see, there's a 3 there, and then that will make that a 4 there over 4 pi. So where will that be? Where will that occur? Alright, well, man, that's difficult. What we can use to simplify this problem, and maybe so we can use maybe a inverse sine function or an inverse cosine function, one thing that we can do is use a trig identity. The trig identity that we can use for this, the product to sum formula, right? So I have sine times cosine. It is defined as this guy, right? And if both of them are x, I'm going to have, here it says that sine of u times cosine of v is equal to 1/2 times the quantity of sine of u plus v plus sine of u minus v. If u is x and v is x, then sine of x minus x is sine of 0, so that's going to cancel, and I'm just going to be left with 1/2 sine of x plus x, which is just 2x. So sine of x times cosine of x is the same thing as 1/2 sine of 2x equals 3 over 4 pi. So I can multiply both sides by 2, and I get sine of 2x equals 3 over 2 pi. So let's bring that right over here. Actually, you know what? Let us increase our canvas size so we get a little bit more working room. And we can erase this guy right there and bring it down a little bit further. There we go. Sine of 2x equals 3 over 2 pi. We can take an inverse sine of both of these as long as we remain in the interval that we are considering. Right? Our interval that we are considering is from 0 to pi over 6. The domain of inverse sine will give us out values that will equal the value that we put into it. Excuse me, it will equal the value that sine has to be, the input to sine has to be in order to get out 3 over 2 pi, as long as this number is contained in an interval of negative pi over 2 to pi over 2. And 3 over 2 pi is a value of 0.477 something something. So that is well within our bounds of 1.57 being pi over 2. So this is in the domain of the inverse sine. So this should give us out inverse sine of 3 divided by pi divided by 2. Right, which is 0.49 something 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 something. So x equals 1/2 of the inverse sine of this thing, which is approximately, take half of that, 0.2488. Okay, let's make sure that we have the right thing by going to our graphing calculator. So we plot our original function, f, as 6 times x divided by pi, and we'll use just a decimal approximation for pi, 14159265359-ish. Let's see, and then minus 4 times sine of x quantity squared. And we'll go from our interval of 0 to pi over 6. So take pi divided by 6, you get 0.52359877 roughly. One thing that you want to make sure that you do is set your calculator's mode to radians. Otherwise, you'll get out something which is not good. On your calculator, you should have a little mode button, which you might have to hit like a second key and then like another key in order to look at the mode. And under that, it will say degrees and radians. You should put in radians. If I hit enter here, there we go. So here I have a 0 here and a 0 here, so that's good. And right about at the midpoint of this interval, I see that I have this 0 tangent line that could probably be approximated there. If I figure out what this value of my function is right here, by just taking this value of 0.24888 and plugging it into my original function, I get about a value which is approximately 0.232634-ish. And if I graph that, that is this value that is right here. And you see that this horizontal tangent line passes through, and it looks like it approximates the function very well. Through that point. So, looks like we have the right thing, apparently. So, that's good. In our next video, we'll do another problem from this section.